Welcome everyone. I am Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. I am a PMRF fellow here. So today we are going to discuss sample questions related to assignment 1. And so let's begin. Okay. So let P is equal to A, B, C, D. So this is a poset we are going to discuss. So I hope you are familiar with the definition of poset. Just to recall, poset is a set with a relation which satisfies which satisfy first reflexivity or reflexive property, second antisymmetry, and transitivity. So I hope these definitions you know what is reflexive, antisymmetric, and transitive. Should I explain? Yes or no, maybe? Dheeraj Mahalakshmi.
Yes, ma'am.
Is that okay?
I have doubt in okay, ma'am.
Okay, so I can recall. So reflexivity is if you take x, so for every x, so basically x is less than or equal to x for every x belongs to P. So if you take any element from P is just a set, okay? So P is a collection of elements. So this is a set. So for every x, x is related to x itself. So that relation should be there. Okay, for example, just to if you want to see as a picture, like you can take natural numbers with the relation this less than or equal to. So this relation is in general, like you can define it to be divisibility, you can define it to be something else, but it should satisfy these three properties like reflexivity, antisymmetry, and transitivity. So for example, I am taking natural numbers with the relation less than or equal to. Here it means less than or equal to. Okay, so if you take so 1 is always related to 1, or for example you can take any natural number, n is less than or equal to n always. So if you want to say, like if you take your relation to be just less than, then reflexivity will not be satisfied. So you cannot so this is not a poset if you just take less than, strictly less than. So is it clear what reflexivity means?
Yes, ma'am.
Okay, so you can consider these two examples. Just keep it inside. Okay, so second one, antisymmetry. So that means if x is less than or equal to y and y is less than or equal to x, then x is equal to y. So if means like it should be firstly these two conditions should be satisfied, then we can say that x is equal to y. So here in this set, n less than or equal to, you know that if 1 is less than or equal to 2 and if you say 2 is less than or equal to 1, both condition cannot be satisfied if these two elements are not same, right? So you can just say like if x is less than or equal to y here, if x and y are so in your notes, n represents all the non-negative integers, so it starts with 0, and for positive integers it has been used with this p. Okay, so 1 2 3 like this. Okay, so if x is less than or equal to y and y is less than or equal to x, then this implies x is equal to y. because if one element, if one number is less than or equal to other, then other way around is not possible if those elements are different in natural number. So if you consider that in your mind, so this property should be satisfied. Is that okay? So basically, for two distinct elements, both side relation is not possible. Both side, for if you take just two distinct elements, then you cannot say x is less than or equal to y and y is less than or equal to x for distinct elements. This means that. Is that okay now?
Yes, ma'am.
Okay, great. Okay, third property is transitivity, which says if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. So, uh, if so, for example, in natural numbers again, if you have 1 is less than or equal to 2, and you have again the same element 2 is less than or equal to 5, which is true here, then 1 will be less than or equal to 5. One second. It is not showing, just a second. I'm just trying to connect my iPad, but it looks like there is some problem. Yeah. I hope this is visible. So I said,
Yes, ma'am.
yeah, thank you. So if 1 is less than or equal to 2 and 2 is less than or equal to 5, then 1 is less than or equal to 5. This is true always. So definitely n comma less than or equal to relation is satisfied. So satisfies all these three properties. So this is a poset. So n comma this is a poset. Less than or equal to is a poset. So these are three properties which need to be satisfied for some set to be a poset with some relation. So poset comes with the relation because this has to satisfy these three properties. Okay. So let's see if this happens with our question. So first question says,
Ma'am,
yeah,
ma'am,
yeah.
can you give antisymmetric example number using numbers? Antisymmetric.
Example as in, oh, so this,
Transitive means 1, 2, 2, 5 and 1 less than or equal to 5
yeah,
zero.
yeah, yeah.
So how to write antisymmetric?
So anti-symmetry is basically, it says, so if you take for example this set, this says if x is less than or equal to y and y is less than or equal to x, then x has to be equal to y. This is more of an abstract thing if you see in numbers, because numbers you can directly see that this won't happen, like won't happen as in if you say like 1 is less than or equal to 2. So for example you cannot write 2 less than or equal to 1 in this scenario, because this is never less than or
Ah,
equal to. So in natural,
ah,
like in numbers, the what is happening. So if you go in abstract sense, then definitely this property makes sense. So for example, so for which anti-symmetry is not satisfied. I'm just thinking of that example. uh, mhm. So x is related, so for example just take all the relations, let's say n is n comma some relation. So I'm not writing with less than or equal to because it will confuse you. So let's say this relation is r. Okay, this is your relation, and relation says
Okay.
everything is related. For example, 1 is related to so everything is related means 1 is less than or equal to 2, 2 is less than okay, so I should write r. Relation which has which which says everything is related to everything. So here it means 1 is related to 2 and 2 is related to 1, like less than or equal to, if you are thinking in that term. So 1 is related to 2, whichever like we defined relation to be like this. So 1 is related to 2, 2 is related to 1, then it should say 1 is equal to 2, but that is not true because we said everything is related to everything. So you can write 1 is related to 2, and then you can take 2 is related to 1. Okay, so 1 is equal to 2.
Okay.
So this is very vague very vague answer to your question, but I think like we can find some on top of my
Yes,
head.
ma'am. In YouTube, for examples, I also searched some examples of antisymmetry. They
uh,
wrote 1 comma 1, 2 comma 2, 1 comma 2, 2 comma 1. So I didn't see 2 comma 1. So
uh,
how they said antisymmetric, I don't know. So that reason only I'm asking.
okay, so you are saying what is your example?
Wait, ma'am. She said.
Yeah.
They said it is antisymmetric. 1
uh,
comma 1,
1 comma 1,
2 comma 2,
2 comma 2.
3 comma 3,
Okay.
4 comma 4,
Okay.
1 comma 2,
Hmm.
2 comma 3,
Okay.
1 comma 3.
1 comma 3.
Yes, ma'am.
So basically
This
if
is
you are,
4 seconds.
so so reflexivity is satisfied because all
Yeah.
x comma x are related. So comma means basically you are saying 1 is less than or equal to 1, 2 is less than or equal to 2, 3 is less than or equal to 3. We are using less than or equal to, I should not say less than or equal to, but this is your relation. So that is in general, like you
Yes,
can
ma'am.
take divisibility, you can take anything. It's just a notation to
Yes,
write that
ma'am.
relation. Here
Hmm.
1 is less than or equal to 2, 2 is less than or equal to 3, 1 is less than or equal to 3. Okay, so for example in this set, if you have given 2 comma 1 also, for example you have given 2 comma 1,
Okay.
then these two elements are there. So that means
Yes,
2 is
ma'am.
less than or equal to 1, and 1 is less than or equal to 2. But x is not equal to
Hmm.
y because 1 and 2 are distinct elements of one
Yes,
in the
ma'am.
set 1, 2, 3, 4. So here it
Yeah,
fails.
ma'am.
Yeah. So in numbers it's,
What I am
yeah.
thinking here, reflexive, I know. Transitive also, 1 comma 2 and 2 comma 3, we can write 1 comma 3. That 1 comma 3 also in the set. So the
Yeah.
transitive is okay.
Yeah.
Reflective also okay.
Exactly.
But I don't know how it anti-symmetric. That
So
reason only I'm
yeah,
asking.
exactly. So one thing is there always, like if you are talking about anti-symmetry, so that was your set, right? So
Yes, ma'am.
this was nothing here, right? This was the set. Okay, so
Yes,
here
ma'am.
in anti-symmetric thing, if x is less than or equal to y and y is less than or equal to x, if this property holds, then only you will search for the next thing. So the
Yes, ma'am.
so the something need to be satisfied for x equals to y. So if these two things are not there, then it is vacuously true. So
Yes,
what?
ma'am.
So if so it is given 1 is less than or equal to 2, right? But 2 is not less than or
Yes,
equal
ma'am.
to 1. There is no element of such kind. If there is
Yes,
that,
ma'am.
then you will check if x is equal to y or not. So
Hmm.
i- if the if condition is not there, then we say that this is vacuously true. That is a term for
Hmm.
saying such things like antisymmetric holds because it is vacuously true, like this.
Okay.
Yeah. So if I just put here, for example, if I just put 2 comma 1, then antisymmetry is not satisfied because uh, 1 is related to 2 and 2 is related to 1, but 1 is not equal to 2 because we are separating 1, 2, 3, 4. Like we are saying that these are distinct elements. So
Yes, ma'am.
there it will fail. Okay, very good. Okay, so let's see if so in our question, let's see what is happening. So P is given to be A B C D. So your poset is A B C D, like the set is this with the relation with relations A is less than or equal to C comma D. That means like four relations are given. B is less than or equal to D. So four relations are given. So let's see if this is a poset or not. Okay. Okay, let's try it out. Okay, one more thing. Right. Yeah, so A is less than or equal to C and A is less than or equal to D. I should write one more property here. Uh, that will make sense. So everything is related to everything. So A is less than or equal to A. A is less than or equal to, sorry. So everything is related to itself. I'm adding these conditions. Okay. So you have 8 relations if you count. A is less than or equal to A, B is less than or equal to B, C is less than or equal to C, and D is less than or equal to D. Okay, so these are the relations. Now let's check if everything holds. So reflexivity, everything should be related to itself. Okay, so first property is satisfied, right? First is okay because all these four relations are there. Reflexivity, is that okay?
Yes, ma'am.
Okay, great. Yeah. Okay. Dheeraj, Sadat, you can ask any question if you have in between. Okay. Yeah. And what about antisymmetry? What do you think? For antisymmetry, yeah.
That is also vacuously true because we never have any pair distinct triplet of ABC of the form where A is less than equal to B and B is less than equal to C. So we never have this LHS condition, so we don't need to check RHS for transitivity.
Exactly. So yeah. So that is for transitivity, right? So if x is less than or equal to y, this thing is not there, right? You meant to say about
Yes.
transitivity or antisymmetry?
Okay. Sorry, I jumped to transitivity.
That's okay.
But yeah, even anti-symmetry also we only have we never have the x less than equal to y, y less than equal to x unless x is equal to y.
Yeah,
Uh,
exactly.
so that is also.
Yeah, very good. So both are vacuously true. So antisymmetry is done because you don't have both side relation. So among these 8, x is less than or equal to y and y is less than or equal to x is not there for x not equal to y. So antisymmetry is done, and similarly transitivity. So if you are thinking about these cases like A is less than or equal to A is less than or equal to C, this implies A is less than or equal to C. So there is nothing new in this because you have this equal. The second one is giving your main thing. So it's nothing compared to like new thing. Okay. So yeah, you can say that this is true. So reflexivity, antisymmetry, and transitivity is done. Is anybody have any question on this?
No, ma'am.
Okay.
Yeah.
Okay, great. So, okay, scrolling vertical. Yeah. So this is a poset. So that is true. Nice. Now, let's check about whether it contains a chain or anti-chain. So just to okay, what is a chain? Do you remember the definition?
Yeah, so basically every pair of elements, we have either x is less than equal to y or y is less than equal to x.
Exactly. So every so a subset maybe a subset of poset P with the relation. So the relations are same. Is is a chain if if uh, every pair is comparable. So we can say in this term also. So exactly what you said, if you have x and y belongs to subset, let's say you are saying denoting by C. So x and y belongs to C, that means either x is less than or equal to y or y is less than or equal to x. So whatever we have, all the pairs we have in the chain, all are comparable. So either x is less than or equal to y or y is less than or equal to x. Exactly. And anti-chain is just opposite of this definition. So a
If
subset.
x is less than equal to y, then x equals to. So
Uh,
element is only comparable with itself.
yeah, so you can say all the pairs are incomparable. So nothing is comparable. So exactly. So every pair is incomparable. So I should write full definition. A subset C dash of is a chain is an anti-chain if every pair is incomparable. So that means if you have x and y belongs to C, then uh, distinct. Then, sorry, then neither this is true, although this notation we don't use, but yeah, it is incomparable. So as he said exactly, we can actually write in the sense of if x and y belongs to C, and and x is either this or x is the greater than or equal to y, then x is equal to y. So two distinct elements are incomparable. Okay, very good. So yeah, for our question it has been asked what is a chain. So which of the following forms a chain. So if you take a comma c, let's see if what do we have. So we have these relations. So what do you think about a comma c?
It's a chain.
It's a chain, exactly. Because we have a relation a is less than or equal to c. So elements are comparable. Okay? All the elements are comparable. So there are just two elements. So there is a relation between a and c. So we are done. What about ACD? Is this a chain or is this an anti-chain or
It's neither of them.
exactly? So can you explain?
That is because if you take the element A comma D, they are incomparable. So we can say the given set is not a chain. Similarly, if you take the elements A and C, they are comparable. So we can conclude it is not an anti-chain.
Exactly.
Hence, it is neither of them.
Very good. Yeah. Very good. So, sorry. Yeah, A and D are incomparable. So it says that this is not a chain. And in this only. And A comma C are comparable. So this says that this is not an anti-chain. So this is neither a chain nor anti-chain. Exactly. Very good. What about A comma B? Yeah.
It's an anti-chain.
It's a anti-chain. Okay, very good, because there is no relation between A and B. So there is no relation between A and B from these relations. So we are done. So this is not a chain, or you may say this is anti-chain. Okay. Does anybody have any problem in this? Feel free to ask. Okay, looks like there's no problem. Okay. Okay. So you are familiar with Hesse diagram, right?
Yes, ma'am.
Okay. So I'll assume you know. Determine all the maximal and minimal elements of the set whose Hesse diagram is given to be like this. So A, B, C, D, E, F. This is your set, and these are the relations. So relations as in, so in Hesse diagram, if you have a H, so that means, for example, E covers C. So E covers C means, sorry, C is less than or equal to E, and there does not exist any, let's say, H belongs to your poset P. So I'll just write P such that C is less than or equal to H, or and this is not equal to, okay, there does not exist any H which is H belongs to P, and H is not equal to C or E, such that C is less than H less than E. So there is no in between. So that is, then we will have a H in your Hesse diagram. Okay, is that clear? I hope. Okay.
Yes, ma'am.
Great. So let's see, what do we have? Determine all the maximal and minimal elements of the poset. Yeah. So determine all the maximal and minimal elements of the poset whose Hesse diagram is given to be like this. So maximal element means you need to find out an element. So let's say, or maybe I'll write X is a maximal element. If for every y such that y is less than x, sorry, I'm writing other way. For every y such that x is less than or equal to y, we have x is equal to y. So basically, if you have any other element which is bigger than like staying above x, and there is a relation in between, there is a relation, so there is a y, there is a x, and you have this h, so that means x is equal to y. You cannot have such kind of element. Okay, so this is then it is said to be a maximal element. and you may have many maximal elements in your poset. Okay. Similarly, minimal element, X is a minimal element. If you have any doubt, just stop and just stop me and ask. If for every y such that now you have this side, we have x is equal to y. So if there is any element staying down to this element, so you have x, you have y in your Hesse diagram, then these two elements has to be equal. Okay. Okay, so can you tell me from these definitions what are your maximal element and what are minimal elements?
Maximal are B, E, F, minimal are A and D.
Uh, Come again, sorry. So
Maximal are B, E, F.
D.
No, not D. B for Bombay.
Oh,
E,
right.
F.
B, E, F, exactly. Yeah.
B, F. Minimal are A and D.
Minimal are A and
D. D for Delhi.
Okay, is it? So
No, sorry, only A.
only A. Yeah. So okay, so as you said, so for B, so you have B, so I'll change the color. So you have B, E and F, because there is no element above that, it is definitely a maximum. These are definitely maximal elements. Okay, so as from the definition it is clear. Do you have any question on this, anyone? These are maximal elements.
Yes, ma'am.
Is that okay? Okay, yeah. So for minimal element, you should have something which is very like at the end of your Hesse diagram. So this is just a. There is no edge going down from here. So this is your minimal element, right? So basically from the definition there is no element in this. If you have any confusion, all the relations you have is like this: D is less than E, C is less than this, and you have AD and AB. And from the transitivity you will get, for example, A is less than or A is less than or equal to D and D is less than or equal to E, so you will get A is less than or equal to E. So at least for cover thing you have these many relations. Okay, so right. So yeah, so you have maximal and minimal elements. So I hope this is clear. And what about greatest and least element? So greatest should be, so from the definition I'll just okay, yeah. So greatest element means you have any element x is uh, uh, actually x is x so there is at most one greatest element, so there could be or there may not be, but it will be at most one. So x is a greatest element if for every y belongs to P, y should be less than or equal to x. So it should be bigger than everyone. And for the least one, x is a least element if for every y belongs to P, y is other side. So you have x is less than or equal to y. So these are the definition. There is a difference between these two, that here you have to first you should have first a relation to satisfy, like y should be if y is less than or equal to x, then x is equal to y. Here for every y it should be true, like for every y should be less than or equal to x. So you understand the difference, right?
Yes, ma'am.
Okay, so can you tell me here what are greater, if there is a greatest element or not?
No, ma'am.
Exactly. Can you explain why?
Since like for example, for greatest element, if it exists, it has to be a maximal element, so we only need to check amongst the maximal elements. Now
Exactly.
let's say we take B, but now B is incomparable with E, and so E cannot be greatest. Like for it to be greatest, it has to be firstly comparable with every other element, and similarly none of B, E, F, they are comparable with each other, so none can be greatest.
Exactly, very good. Yeah. So if there exists some element, let's say x, then it should be less than or equal to b. Sorry, it should be greater than or equal to x. Sorry, b. And similarly, you should have all these relations. If you can have it, then you are done. But that is not true. Exactly. Very good. What about least element? So there is no.
A.
A.
Yeah, A.
A,
So
ma'am.
exactly, very good. So because there is just if you have one maximal element, then you can definitely say that is your greatest element, because there is nothing to check, because those are already on the above line. So if you have one, then those are greatest or least. Exactly. So there is no greatest element, and A is the least element. I can say the because there is just one. Okay, very good. Okay, so I hope this is clear. If you have any doubt, let me know. Okay, so let's move to the next question. Let P is equal to, so P is given to be your 1, 2, 3, 4, 6, 24, 36, 72. So P is given to be this set, and define the partial order by like if x is less than or equal to y, if x divides y. Okay, so I may write x divides y. Notationally we can write like this. Okay, so x is less than or equal to y if x divides y. That is your relation. Now clearly this is a poset. So basically you know that reflexivity is there because every element divides itself. So I can just write x divides x. Okay, and 0 is not there, so there is no issue. So x divides x for every x belongs to P. Second property, antisymmetry. So if x divides x, x divides y and y divides x, so you know that uh, so it has to be equal because it cannot happen for the divisibility. Third property, x divides y and y divides z. If that happens, then so x divides y, that means or if you want to write in terms of like y is equal to rx, you have this from the first property. From second, where r belongs to some I should not write so I can just write P. So P is your set 1 to n, not 1 to n, 1 to up to so on, all the natural numbers. And similarly y divides z, that means you can write it to be so s x s y maybe, and again y s belongs to P. Okay, I'm writing very vaguely. So you have y is equal to some rx, you have z is equal to sy, and where r and s belongs to your natural numbers, then because we are in good condition, we are with natural numbers and everything, because p is just the numbers, then we can definitely write like this. So z is equal to s, y is equal to rx, so you have s rx. So definitely you have this implies x divides z. Okay, you can verify like this. Okay, so transitivity is there. So with divisibility, there is no issue. That is always a partial order relation. Find the number of ages in the Hesse diagram. So you need to find the number of ages. So firstly, you need to construct your Hesse diagram for this set. So okay, let's start. Maybe we can start like from here. So you have 1 here definitely, and biggest number can go here at 72 at this upside. Or maybe let's see, I'll change the color, that is better. Okay, let's start by 1. So in Hesse diagram, you know, the number which is the age will come only if it covers the number which is down. Okay, so for example, you have 1 2, so you will have 2, because between 2 and 1 there is no other number, right? So there will be a age. And now what about 3? So you can 3 is not related to 2, so you can actually write here. And between 3 and 1 there is no other number, because just you can see this is the prime divisor. So like 3, if you divide by 1 to 3, you will get 3. So there will be no other element. And it should belong to P. That is also a condition. Is that okay? Is that okay?
Okay.
Okay. Now let's go up. Now what do you have? 4. Okay. So about 4, you know that you can write above 2. And what about 6? 6, you know, it is related to both of these. So you have this. So whenever you have this divisibility by like multiple of just a prime number, then you can connect basically. So you have 3 to 6. So for example, you cannot connect 4 and 1 directly, because between 4 and 1 you have 2. So 4 does not covers 1. Okay, so there is 2 in between. And after 6, what do you have? 24. So 24, if you write here, I'll write. So you have 24. So it is connected by 4. It is connected by 6. And remember here, 4 into 6 is 24. But there is no other number. Like for example, 4 into 3. So you don't have 12 here. So 24 covers 4. Am I saying right side? Yeah, 24 covers 4. Right? So there is no 12 here. So there is no issue. So it should belong to your poset firstly. So 12 is not there, then we are okay. Okay, and after 24 you have 36. 36 it should come. So 24 doesn't divide 36, so you can actually write, and 4 divides 36. So maybe I'll write like this. So you have 24, so it is connected, and from 36 it is connected, and you have 72, and it is connected from both sides. Is that okay? This is your Hesse diagram for this poset. Is that okay, or should I explain again?
Okay, ma'am.
Okay.
Okay, ma'am.
Great. So this is your Hesse diagram. Now it has been asked, find the number of ages in the Hesse diagram. So you can just count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 ages in the Hesse diagram of maybe P and divisibility. Okay, very good. So just remember, you just put the ages only if it covers the other number. Okay, that's why count is important. Okay.
Ma'am, wonder,
Yeah.
is there any other way to count the edges in the previous question, without drawing the Hasse diagram, like if the number is very huge, for example, if the P set has say 100 numbers, then in that case, it is very tedious to draw the Hasse diagram and then count the edges, right?
Yeah, that is true. But okay, so for example, in this poset, 12 number 12 was not here. Okay, so for example, if you have okay, I'll take one poset which contains all the divisors of 100. So for example, you have this, then maybe you can get a formula, because divisors of 100 are something like a very precise value, like uh, what do we say, Euler's, am I saying right? Yeah, Euler's function. So this phi of 100, so you have a precise number for that. And so in that case, maybe you can count the formula directly. But for example, in this question, 12 was not here, so you have to figure out what exactly are the problems with this. So like if you for the fixed things, like for example divisors of 100, you can definitely get a formula to count the edges. But yeah, I guess for this example you can definitely form a formula. But for the random poset, you might need to calculate precisely.
Only using the Hasse diagram.
Yeah, Hesse diagram is actually better in the sense that other than that, what you will try to calculate, so you will try to calculate what are actually number of covers, basically pairs which covers. Okay, so x comma y such that x covers y, you need to count those pairs basically. So in that case, you're just doing this thing only, you are just calculating like you're just forming Hesse diagram in your mind, I guess. So
Yes.
yeah, so basically if you have something very precise or very known, something which is very known like divisors of 100, you can get something like what are the prime numbers. So basically here what I was doing, I was just checking if in this these if the divide like if you divide 2 1 by 2, then you will get prime number 2. Here 3, here 2, here 3, and here 2, and here for example it is 6, because 12 is not here. Otherwise if 12 was there, then you will put 12 in between and you will have 3 and 2, right? So you can just count all the prime numbers. So in that case you may actually count without constructing this Hesse diagram, I guess.
Okay.
So, yes, you can write the formula, no doubt, for something which is well known or which has some pattern. Basically, if you have pattern, then you can do induction kind of thing, or many things are possible. You can get it, I guess. Is that okay?
Okay, ma'am. Thank you, ma'am.
For random thing, like definitely you need to calculate properly. Okay, but this question is actually just saying like Hesse diagram, like what exactly should be the ages in a post set. So just to understand. Okay. Find the cardinality of largest anti-chain in the following Hesse diagram. So you have given this Hesse diagram. So many questions are related to Hesse diagram, because it is very nice in the sense that you can actually relate graph theory to it, and you can actually visualize it. Otherwise these are just abstract conditions you have, relations you have. So it is better to always have a picture. So find the cardinality of largest anti-chain. Okay, so in the following Hesse diagram, so let's see what anti-chains you could have. So here these lines, these edges is actually saying that G covers B, B covers A, like this, right? So what do you think? Like just pick any of anti-chain. Can you tell one anti-chain here?
ACD.
ACD, exactly, very good. So you can take ACD is one anti-chain, because
Go ahead.
Oh, this is Siri. Yeah. So you have because A is not related to C is not related to D, and D is not related to A. So everything is incomparable. So this is an anti-chain. Very good. And okay, so you have to basically see what are all the anti-chains, and you have to uh, pick the largest one, and you have to say the cardinality. That is the question. So right, so can you see in this ACD, can you put anything extra so that it is still be a anti-chain in ACD?
No, no.
Exactly. Because if you take A, C, D, so you cannot take B because A is related to B. You cannot take G because C is related to G. And again, F and E you cannot take because D is related to F and E. So you cannot put anything extra to make it to keep it still a anti-chain. Okay, so in this case you have just the biggest one with ACD basically. So let's see if you have anything else. Okay, so can you pick anything else?
GFE.
GFE, exactly. You can take GFE. So you have GFE. Again, let's check if you cannot put A and B because this is related to G. G and you cannot put C because G is like G is related to C, and again D is related to F and G, so you cannot put anything extra. So this is the anti-chain in terms of this biggest thing. Okay, and anything else?
AGFE.
A, okay, AG. So you cannot
FE.
put A and G because you have this relation. So you have A is related to B because B is above A, so you this B is bigger, and you have B is less than or equal to G. So because of these two things, transitivity says A is related to G, right? Yeah, so no problem. So this is a relation already, so you cannot put G with A. So if A is there, so let's see what other things you can put. So B you cannot put, you cannot put, C definitely you can keep. Again you will get, I guess. Oh yeah, nice. So if you have C,
ACFE.
yeah, F.
ACFE.
You can put F and E exactly. As you said. So you took A, and now you took C because that is an option because C is not related to A. Now if you take F and E with these two, then it is okay because nothing is related to anything here. Is that okay? Do you have any question on this?
But A is less than or equal to no. Yes. Okay.
Yeah, because
Correct.
these are other ages, so you can consider F and E and separately A and C. So yeah, that is, I guess, biggest because again we can check all the possibilities. So you have, so basically when you have A, you can put C, F and E and nothing else, and you have tried AC with D, so you have tried all the options with A. Now if you take anything else, I don't think you can get anything better. So basically this is calculating from the figure itself. So whenever you are doing such kind of questions, pick something. So for example, you have picked A. Now try all the possibilities you have. So when you are done with this, you can try with any other element, and you try with everything, so that you will not so all the possibilities will be checked. So that is the most important thing, right? So I'm saying this is your maximal. So maximal is in this largest. So basically we need the cardinality. So largest anti-chain has cardinality 4. Okay, is that okay? Do you have any question on this? Is that okay? So basically,
Okay, ma'am.
okay. So basically, just pick one element and just try to check all the possibilities. So for example, as I said, you start with A, now put maybe B, and so B is not a possibility, so you can actually order first. So basically here A, B, C, D, E, F, G, so you can just keep that in mind. So you have tried B, no, that doesn't work, so you put C because that is a possibility. Now after C you try with D, so D is a possibility, and now after D you cannot put anything, so you are done. So now after these two elements, try, do you have anything else, because you start with the last thing. Okay, so D was the last thing which you have considered. Now replace D by something else which you can possibly take it. So after D you can take so A, C, B, D, and now you will try E, for example E. So after E you can again you can take F, right? You cannot take G because C is related to G. So you are done with this. Again, when you have taken F, A, C, E, when you have taken F, can you pick anything else other than F? That is not a possibility, so that is okay. Okay, so A, C, now you cannot replace E, so F, so again you come to E. Now if you take anything else other than E, so other than E means E, F, now you will take F. Again if you take F, you go above that, so after F you have option only of G, so that is not a possibility, so you will just get this, right? So these are all the options you will, so like this you can order it and have all the values. So that is kind of so that is a way to, so whenever you need to check all the possibilities, you should always go with the pattern. That is important, so that you will not uh, like all the options will be considered in that case. Okay, great. Okay, now in the above question it has been asked mu p of ag, can you calculate that? So okay, I'll just, okay, maybe, so you have this, okay, so I'll just remove these things. Okay, yeah, so what has been asked, mu p of, so Mobius function of a comma g, so this has been asked. So from the definition, what do you know about this? This should be, so for I'll write it in general. Mobius function of x and y is equal to 1 if x is equal to y. I can make it bigger. Minus of summation mu p x comma z, where this is the relation, if x is strictly less than y, and you have 0 otherwise. If there is no relation between x and y, then 0, right? And even if x is greater than y, so in that case also this is 0. So this is the formula for Mobius function, right? So let's calculate in this scenario. So you have a comma g, you need to calculate mu p of a comma g. So since you know a is what is the relation between a and g, so you have a, b and g, this is your connected thing. So you know a is less than b and b is less than g, less than or equal to g. This implies a is less than or equal to g. So these are related and these are not equal, so you have the condition x is strictly less than y. So from the formula it should be a z and this is g mu p of a comma z, right? Now let's calculate what is the summation. So all the z such that a is lesser than that, so a is less than or equal to z, and that should not be equal to z. So let's see what are all the options for z. So you can consider z to be a because a is less than or equal to a. So you have minus, let's take a bracket, minus, you have mu p of a comma a first. Then what do you have? You can take a to be something else. Now what is the other option such that this property holds? What value can you take for z other than a?
B.
B, exactly. Very good. So you can take a comma b. So you can take z to be b. And can you take anything else? So anyway, closed it. But if you have, for example, this is not here, but let's say if you have something like a is related to c also, then you will put mu p of a comma c. So you have to consider all the ages. Okay, so here a b and ac, if that is a age, but this is not here, so I'll just remove it. Okay, right. So let's calculate. Firstly, now mu p of a comma a, now you have to again use it. It's like a recursive formula, so you have to again use again use the formula for mu p x comma y. So a comma a, so a, these are same, so the value should be 1, right?
1.
Yeah. And what about this? Now we have to calculate this one, right? So let's see what is this. Mu p of a comma b. So that should be what? Now you know a is less than b, right? Here in your figure a is less than b. So from the formula it should be a less than or equal to z less than b and mu p of a comma z, right? Now what are the values of z we can take here? So all the in between things and even a also, right? You can take a. So minus of mu p of a comma a. Can you take anything else? Like, is there anything?
No.
Right. So you have, because the b covers a, so there is nothing in between. So you have this, and this is equal to minus 1 because a comma a, mu p of a comma a is just 1. So you have mu p of a comma b turns out to be minus 1. Right. You will get minus, and this is 0, so you got 0. So that is your answer for this question. So remember, you have to consider all the ages. So don't forget, for example, if you have given this, or maybe more than that, then you have to consider all the possibilities like mu p of a comma c, mu p of a comma d, like this. Okay, is this clear how to calculate Mobius function for basically an interval?
Yes,
okay, great. Yeah, okay, let's move to the next question. Okay, so this is a question related to product of Mobius functions. Okay, and yeah, bell numbers. Consider the poset pi n. So basically pi n from the notes, if you know, these are the partitions of n. So this represents partitions of, so this is the set of all the partitions of n. So for example, you have 1 2 3 4 5. For example, if I just take this, then if you have basically n equals to 5, then what are all, or maybe I'll just take it something lesser than that. So let's take n equals to 4. Then what are all the partitions you can take? So you have 4 elements you can take. Okay, so for partitions, so basically what are all the partitions you can have? This is one partition. Partition means you divide the set in whichever number, and the union should be the whole set. Okay, and those should be disjoint. So that is the partition. So partition of n means okay, union of, for example, ui, I is equal to 1 to, for example, any k, and these should be disjoint. So this is a notation for disjoint, maybe like this, or just square kind of thing. Okay, so you have this partition. So what are all the possibilities you can have? So you have 1 2. Again, you should go with the pattern so that you will not forget anything. So what I started with, okay, I take it. Okay, I'll this should not be. Can I take just a lesser one? That will be better. Okay, because I need to just write the notation. If you don't know from the notes, then I'll just write it like this. So you have 1, and now you club 2 and 3. That is one possibility. So you are done with the singleton one. Now you can take this and maybe this, and you have 1 3, and you have 2 separated, and the last one 1 2 3. So okay, I should not write set outside. So these are the elements of this partition. So pi n pi 3 contains 1 2 3 4 5. Okay, this contains these 5 elements. Okay, so as a notation you can actually write it like 1 2 3. So this these are blocks. So blocks means you have like elements from the set which are in the same set. You will write it in the same block, like this. And okay, there is a order to write also. So you start with the, so least number should come in the at the first place. So for example, you have 1 here. So the block which contains 1, it should be in the first block. Here again you will write 1 2, and here 3. You write 1 3. So yeah, 1 3 and 2. So here if you see, so block which contains 1, it should come in front, and then which contains 2 will be the next one. And if it is in the same one, like for example like this, then the next least number will come in the next block. And this is 1 2 3. So this is the representation, like this is a way to write partitions, so that is easier, because otherwise there are too many curly braces. Is that okay? This notation is clear, I hope. This is from the notes only. Yeah, very good. Okay, so this is your pi 3. Now let's see what do you have. And yeah, partially ordered by refinement. So the order, the relation, so in this partition set, you have the relation to be like, okay, so the refinement should be in the downside. So for example, if you see here 1 2 3, now what you have done, you have clubbed 2 and 3. Okay, so club 2 and 3, so it is above this. So basically 1 2 3 is less than 1 2 3. So the down one, like the which is on the left side, it should be the refinement of this one. Okay, for example, can you tell me what should be the relation between this? Can you tell me what will be the relation in between these? Or maybe there is no relation?
There is no relation, right?
Yeah, exactly. So there is no relation because this is not the refinement, Balki. This is like this 1 3 is there, and there is no 1 3. There is no set which contains 1 3 in single set. So there is no relation. So that the left side one should be a refinement. Then only we can have the relation. So here if you see 1 2 3 will always be on the upside. 1 2 3 comma I've used like this. So I hope this relation is clear. Okay, because if this is clear, then we can move forward. Okay. Okay, if you have any doubt, okay, 1 2 3 will always be on the left side for everything because it is related to everything. So this is your least element also, because there is just one element which is of such kind. And similarly you have the greatest element, which is 1 2 3, because it will stay. Okay, I can write like this. Okay, I can now you can see that Hesse diagram will help me. So okay, I'll form a Hesse diagram for this. So you have 1 2 3 and you have 1 2 and 3. Here you can take 1 2 3, just take all the partition, all the refinement you can do here. So you can do this, you can do 1 and 2 3. Now you can again, okay, now you can just do this. Yeah, nice. So you have 6 relations, 6 covering relations, like there are many, but at least this. At least you can say these relations, these 6 relations generate the relation set for this PO set. So there are terms for in groups, these generating and like this, that helps. Okay, anyway, so I hope this is clear. So these are the relations we have. So let's go to a question that says you have n equals to 9. You are considering pi 9 now. That is a very big set. And x is equal to, I just take this. Or maybe I can just take full question. Okay. Right. So you have this. Okay, what has been asked? Let's see. X is equal to, x is given to be 1 2 5 3 8 and 4 6 7 9, and there is y 1 2 5 3 4 6 7 9 and 8. So then which of them are comparable? There is z also. So let's see first. Maybe I'll write 1 2 5 3 8 4 6 7 9. So can you tell me which are comparable with these?
XZ and YZ.
Sorry, xz and yz. Very good. So can I write like this? Exactly, very good. So as you can see, firstly let's check if x and y are related or not. So you have 1 and 2 5. So you can see there is a refinement of 1 to 5 in x. But if you see 3 and 8, so you have said x is a refinement. So basically this is on the left side. And now if you see 3 and 8, you have 3 8 together in x, but you have a refinement in y. So definitely you cannot go both sides. So these are not related, right? So you cannot say x is related to x is less than or equal to y, because this is okay, 1 to 5 is okay, but 3 8 will be a problem. So it should be a refinement. So 3 and 8 should be in the different sets. So there is no relation in this kind. And on the other side also, if you take y and x, here again, so 1 to 5 is a 1 to 5, sorry, 1 and 2 5 in x is a refinement, so this won't work. So basically there is no relation between x and y. Now what about x and z? So here if you see 1 to 5, in x 1 and 2 5 forms a refinement of 1 to 5, that's okay. And also 3 8 4 6 7 9, and this, so this x is a refinement because 3 8 and 4 6 7 9 is a refinement, and this is in a same set in z, so this is okay. And what about y? So we have checked x and y are not related, so let's see y and z. So 1 to 5 is same, okay, and 3 and 8 has been clubbed in z, so basically that is okay. So yeah, So y and z are related. It doesn't matter how you write the numbers in the same set, because this is just a set, this is not an ordered set, so there is no issue. So we are just partitioning it, you can write it in any form. Okay, is that okay? These two relations, there are just these two relations between x, y and z.
Okay, ma'am.
Okay, great. So which of them are comparable? We are done. Let's see what is the second part. Okay, okay. You have for each interval PQ in part 1. So you have got two intervals, x, z and yz. So these are only relations. You have these two intervals in part 1. Determine the values of ni such that pq is equal to product of pi ni. So this is a formula if you know from the notes. So okay, so xz, so x is given to be, I'll write it again, 1 2 5 3 8 and 4 6 7 9. And you have y 1 2 5, sorry, not y. Okay, anyway, we need y. Let's write z first. 1 2 5 and 3 8 4 6 7 9. So so basically x and z, so this interval you can actually write it from, okay, I'll write the values again. So you can actually think of it as the product of different partition sets. Okay, so what does that mean? You have so what do you have? So you have 1 2 5 and here 1 2 5. This is this difference you have, this refinement you have. So basically if you think in your you can think it like this. So you have separated two things. So for example, how shall I say, okay, the only option you can club it. Okay, so for example you have two elements 1 2 and you can just make it in the one set, in set 1. Okay, so you have this and this, so you have just this option. So basically the number of refinement, like the number of refinement from z to x, this will give the value of these ni's. So this is actually from this part you have just pi 2. So pi 2, like if this is from the notes and writing like this, but if you want to intuitively think of it, so you have just, for example, 1 2, you can only club it. And what is pi 2? Pi 2 is all the partitions of 1 and 2. So these are only two partitions you have, right? So this is the way, like this is so you can consider 2 5 as one element. So for example, let's say 2, and if you want to say 3, so you have just two elements 1 and 3. Now you can only club it. Okay, there are just two options. So pi 2 is basically there are two elements. Okay, yeah, so there are just two elements, so that's why this pi 2 comes. Is that clear, like how exactly it has been isomorphic to this? So for example, if you just have this 1 2 sorry 1 2 5 and 1 2 5 like this, you have one element and this is other element, then it will be just isomorphic to pi 2, because there are just there's just one break in between, right? So is that clear? Is that
Yes,
clear?
ma'am.
Okay, great. So can you tell
I've
me?
wondered,
Yeah, yes.
won't you include that x and z as well? So there will be 4 elements, right?
Uh, come again. So four
Won't
element.
you won't you include that x as well as z in the set?
Mm-hmm. So
So there will be 4 elements totally, right?
yeah, you mean about this, the other part?
Yes, ma'am.
Yeah, so other part I'm writing. I just talked about 1 and 2 5. So that's
Okay.
why there is a cross here. So I am going to
Okay.
write
Okay.
the other part. So what is other part? Other part says you have 3, 8, 4, 6, 7, 5, 9, and you have just clubbed it. Again you have the same thing. So you have 2. So basically count the number of refinements you have for each bigger side. Okay, so you have this two parts, and 1 to 5 has been refined in two sets, and 3, 8, 4, 6, 7, 9 has been refined in two sets again, right? So from those you will get pi 2 cross pi 2. So for example, okay, I can go with x and z also, y and z. So let's okay, I'll do y and z also. Okay, so you have one, you will get more intuition. You have 1 2 sorry, oh. So y is 1 2 5 3, 1 2 5 3 4 6 7 9 and 8, and you have 1 2 5 3 8 4 6 7 9. You have this. Now can you tell me what will happen here? What should be the thing? What should be pi is here? So pi is partition set again, like partition of 2, square bracket 2, that means the set 1 2. So again think of the same thing, like you see 1 to 5 is there, so just check from the bigger side, start with the bigger side, and 1 to 5, let's see is that refined or not. 1 to 5 is exactly same as the same thing, so previous one. So you have just pi 1 you can write, it doesn't matter because that is just one element, so you are going to write cross thing. So 1 to 5 is there, that has not been refined at all. Now let's see what happened with the other thing. You have 3 8 4 6 7 9. It has been refined in three parts, like separated in 3 4 6 7 9 and 8. You have three partitions for this. So basically you have three partitions of this. So this you can think of 1 2 and 3. So you have the set 1 2 3, it has been refined in this. So you need to count all the, so you have 1 2 3 separated, you have 1 2 3. Now you will take all the refinements possible. So you will get 1 2 3 1 3 2. Basically interval is what? Interval takes all the values in between, right? So you have 1 2 3. So you got all the pi 3 values. Okay, so it just, you need to count in how many parts it has been refined. Okay, so you have 3 8 4 6 7 9, it has been partitioned in three sets. So that's why you have to consider pi 3. This is, you can think of it in that sense. You can actually define a relation. So as I said, I took 1 2 3 in place of this and this and this. You can think of it 1 2 3 like this. So you will get pi 1 cross pi 3. So what I meant, you, for the isomorphism you need to define a bijection first, p to this set, for example product of this pi i's or maybe n i's I write, if you see the notations from the notes. So it's like this. So you will define a bijection between these sets, and then you will actually and what should happen if you defined phi. So for isomorphism, what should happen? So this is the definition of isomorphism. So isomorphism says you have a isomorphism phi between p to this product if x is less than or equal to y, then what should happen? Phi of x should be less than or equal to phi of y. This should happen. So that is your isomorphism. So then if this is a bijection, okay, then phi is an isomorphism between posets. Okay, isomorphism of posets. So that is your definition. So you can rigorously actually check whether this is isomorphic to this or not. So so as I said, intuition is exactly this. Even the proof will be like this. You take 1 2 3. So here what is this? You have 1 2 3. Here you have just 1. So you can just take it like you have, for example, this element 3 4 6 7 9 8. You the map should be, this element should go to what? Go to 1, for example, this set, comma, now cross, this is like cross. So 1, oh, I should not write this pair, I mean. So from pi 1 you take singleton 1, and from the other side, as you can see, this has been partitioned in 3. So what should you take? You should take this. I don't know if so this representation itself is partition, so that's why I'm not using curly braces. Or you can actually remove this. So this is 1 is in the notation of this divisibility kind of thing. Okay, 1 not slash, this is vertical in LaTeX, I don't know. So 1 vertical 2 1 vertical 3. So it's like this. Okay. So you can actually give this bijection like this, and you have the interval. So this is y comma z is an interval, so you will have all the possibilities in between, right? You will have this. Now you can map it to 1. You will map 1 always, because 1 to 5 has not been splitted at all. So you will have, what you have clubbed, you have clubbed first and second one, so you can just map it to like this. So similarly you can continue, and you can, the last element is 3 4 6 7 9 8. You can just map it to 1 comma 1 2 3. So this bijection you can take, and you can check that this will satisfy 5x is less than or equal to 5y whenever x is less than or equal to y. Is that okay? So
Okay,
in simple terms, as in like just for the calculative purpose, you can just check what is the that set has been refined in how many things. So for example, if you have 1 2 3 4, I'm just taking random example, 5 6, let's take till 7 8 9 10. For example, you just have till 9, and the other element is 1 2 3 4 5 6, and you have 7 8 9. Firstly, these are whenever you are talking about interval, you are already saying that this is less than or equal to y, so this has to be a refinement. So it should be isomorphic to, can you tell me now, what should be the
pi 3 cross pi 2.
Pi 3 cross pi 2.
Exactly. So this has been clubbed, these are 3, so refined, this set has been refined in 3, and this is in 2 exactly. So we are done. So I hope this is clear now. Very good. So this is an isomorphism in terms of both sides. Okay. So okay, for yz you have now this, and for xz you have this. Okay. Now let's see what is the third part. So that has been asked, like, can you give the values of ni, which we gave already. Okay, I'll again snip. Now you need to calculate the Mobius value of these. So now we need to calculate Mobius value of these. Whenever you have whenever you have the interval, then you need to calculate mu of pi 9, because otherwise we are done, because whenever you have no relation, then it is 0. Whenever p is equal to q, then we are done. That is just 1. So from the definition, so mu again pi 9 pq, the formula I can write it again, 1 if p is equal to q minus summation mu pi 9, and you have p z. Okay, z has been used, maybe yes, So P less than or equal to S less than Q whenever P is strictly less than Q, and this is 0 otherwise. So that is the formula. Now let's calculate. Right. So again, from the product of Mobius functions, so we have a formula already. If you know, if you can, so if you have, for example, pi z, that is equal to pi 2 cross pi 2. So this is, if that is the isomorphism, then so mu of pi 9. So basically in the isomorphism the value of Mobius function does not change. So that is something which is invariant under isomorphism of posets, and whenever there is an invariant it is very important. So you have x comma z. If you want to calculate this, then it should be equal to pi. Okay, now you have what? So from the so I can just write equality because this is an invariant, because this is just a value. This is pi 2 and 0 hat 1 hat. So this is from the notes. Pi 2 0 hat 1 hat. I can open it also. This one. So from the notes, yeah, we have this formula. So product of mu pi ni 0 hat 1 hat. Okay. So, and from the theorem which has been proved in notes, so the mu pi n 0 hat 1 hat should be equal to minus 1 raised to power n minus 1 n minus 1 n minus 1 factorial. Okay, sorry why this is happening. Okay, so is that formula clear? So I'll just use it for a question. So you have value to be equal to mu of pi n. So this is the least element, this is the greatest element. So this has been proved also in terms of the general values, that product of like Mobius function of any interval is or maybe I can say Mobius function of a poset is equal to the Mobius function. If P is equal to P1 cross P2, then you can actually take the values of mu also in the same term basically. So you have this, and this should be equal to minus 1 raised to power n minus 1 factorial. So in our case, mu of pi 2 0 hat 1 hat is equal to minus 1 raised to power n is equal to 1. This is 1, this is 1 minus 1 factorial. Was that the formula? Anyway, that's just 1. Sorry, this is 2. Yeah, right. So n is 2 because we are calculating pi 2. So 2 minus 1, 2 minus 1. So you will get minus 1. So mu of pi 9 for xz is equal to minus 1 into minus 1. That is just 1. So that is the normal product. And for pi 9 yz, you know that was equal to pi 1 0 hat 1 hat mu of pi 3 0 hat 1 hat. So it should be equal to minus 1 raised to power 1 minus 1 minus 1 factorial into minus 1 raised to power 3 minus 1, and this is 3 minus 1. So this should be, so you have positive here, you have positive, and this is just 1. This is 2 factorial. So this is just 2. Is that clear?
Yes, ma'am.
Okay, great. So that was the question. Okay, let's move to the next question. Yeah. poset on A, B, C, D. So you have a you need to find out. Yeah. So you have the set A, B. Okay, this is a definition. So you have a poset on any number of elements with the relations. If you have the relations like alternative, so A is greater than or equal to B, and then B is less than C, you have just alternate things. Then, or maybe other side, you can have this and this greater, and then again less, again greater. So if you have such kind of relation, then it has said to be zigzag poset. So that these are called zigzag poset. Now, if you just consider A, B, C, D, so we have just taken 4 elements, then definitely the relation, and consider the first relation. So both kind of things could be said it's zigzag poset, but let's consider the first relation. So you have, yeah, C greater than D. So you have this A, B, C, D. Now, can you count the number of anti-chains in the zigzag poset? So you have this zigzag poset with the relation. Can you count the number of anti-chains? So just try to. So again, you have this messy thing, like you have to abstractly write everything. So best is just construct the Hesse diagram. Try to construct a Hesse diagram for this. So you have A, you have okay, A is on in the upper side, so you can just take like this. So you have A here, and then you can take B. Now C should be on the upper side again, okay, and there is nothing in between, because definitely we have given only these relations, so there is nothing in between. Then you take D, okay. So you have such kind of, so that's why it has been called zigzag poset. So you have zigzag kind of Hesse diagram. So can you tell me number of anti-chains in this zigzag poset? Can you count? Now it has been asked how many anti-chains you can construct. So let's try to construct. I need to use chargers, so just try to construct. I'll be back in a minute. Yeah. So, right. So now you have, yeah, can you tell me how many anti-chains, or maybe you can do with me? How many so let's try with one. So can you tell me one anti-chain here?
A and C.
A and C, exactly. So whenever you try to make like A and C, you have just take all the subsets also. So these are also the anti-chains. A, C, or these are also the anti-chains, right? And you can also take phi, like nothing. Empty set also you can take. Okay. So you have, I cannot write, I should not write one. So you have this. Now you can again, so with A and C you cannot add B and D, right? Because that will be related. So now you can just separately take B, right? And then you can take all the subsets. Is there anything else here?
AD.
Yeah, AD. Yeah, I was just searching for one more. Yeah, so yeah, AD. It should be 8. I'll tell you why. So, yeah, so there are 8 anti-chains. Again, for pattern, you can start with one element. Let's say you can always start with 5, and then you can just start with A, and then you just add everything what you need. Now with A everything is done. You try with anything else. Let's say B. Then with B you add whatever you can add. Now yeah, with the AC you can add D also, so it should be here only. Then with B this will be done, and then right, you can go to C, and then after C, with C you can only take A, which has already been taken. And now with D you can just take D, because with B it is done. So this is 1 2 3 4 5 6 7 8. So there are 8 antigens in this case. Okay, can you tell me with what will happen with the A, B, C, D, E? If you take this set, now you have this. Sorry. Okay. Yeah, you have A, B, C, D, E. Yeah, there is no line. Right? You just try to calculate for this. Sorry for asking, like, for calculating things. I know everyone likes abstractness here. But yeah, because there is something interesting here. Let's try to calculate what will be with A, B, C, D, E. So if you take this relation, what can you take? Again, you start with 5. Then you have A. Now you add with A what you can add. You can just start with B, but B will not work. So you take C. And then A, C, can you take anything else? Right, you can take E. And then okay, now can you replace E? No, there is no option, so you move to C. Other than with A, can you take, what can you take other than C? You can take D, right? So D you can take. Then when you have taken D, you cannot take E, so it should be done. And you can take B, C, D, E, so you can take E. So remember, there is no relation between A and E, because there is no age from the downward side. Okay, so you have B. Now you start with B, and with B what can you take? You can tell me. With B, what you can just start with B. Then with B what can you take? You will not go back to A, because that is done. D.
D.
Yeah, exactly. Then you can take E, right? Then B is done. B is done, right? B is done, right? Now you start with C. With C, what can you take? You cannot take D. You can take yeah, E. So C should be there. Yeah, C comma E you can take, right? And then you start with D, and you should be done, because E is connected. So let's count 1 2 3 4 5 6 7 8 9 10 11 12. There is one missing.
Singleton E, ma'am.
Singleton E.
E.
Exactly. Yeah, exactly. So it is 13. Actually, you can also consider like this also. So you have the biggest set A, C, E. Now you just check what are all the options, subsets of this set you can take. That is 3 choose 0 plus 3 choose 1 plus 3 choose 2. How many can you take? And 3 choose 3. So you will consider all the subsets from here. You will get 3 3, and this is 1. 6 and 2 8. So remember phi is counted here, so you cannot count it again. Now you take B and D, so you can see that is the biggest one here. uh, that is one option, but yeah, so you cannot take 3C0 because that is phi, so you have already counted that. So you have 2 choose 1 plus 2 choose 2, so you will get 2 plus 1, that is 3. And now what has been left, so I'm taking the the biggest ones. So you have ACE, you have BD is considered, so you are left with these two ones, B and E. Sorry, CE is already considered, so you need to, sorry, so you need to separately consider B and E. So you just take all the options you have. Okay, so you will get 2C1 and 2C2. 2 plus 1, that is 3. So you got 8, 3. Oh, 1 is considered twice, yeah, because B is already there here, and even E is there. Oh, 8 and 3, 11, and this 14. So okay, some calculation. So what I said, I should
You have
subtract
to
1.
subtract 2 because the singleton be already counted in the previous one, right?
Yeah, so yeah, exactly, I'll subtract 2, but then I'll get 12, right? 8 plus 3, 11, and 3, 14. So I should have 13. I'm just checking where 1 is missing. So exactly as you said, this we should not take because B and E singletons has been considered. But there is one more which has been missing. Okay.
No, instead looking like this, can we look this as power set of B comma E, and then from that just remove empty set and singleton B?
Yeah. Exactly, which we did. Yeah, this is just the counting of power set only. Yeah,
I
exactly. You
think
can see.
there will be only one from this one, and the other will comes from the doubleton set A comma E.
A comma E.
So that will give the other one, so that you will get 14. Sorry, 13.
Come again. Which one you are saying? Which I have left?
Oh, that is already counted, right?
Yeah.
Okay, sorry. That is already counted.
Okay. So this is you should have 2 raised to power 3 here, and now here you should, these are disjoint from the above previous one, so you can just take 2 raised to power 2 minus 1 because singleton we should not count. So there should be 3, it should be 8. Now 3 are left, right? So 3 are left, so from this we should get 2 raised to power 2, but we cannot take, we should remove 3 because singleton empty set, singleton B and singleton E should not be counted, then it should be 1. Okay, there is one missing. Okay. We can check what has been left. Okay, so D and E has been counted.
I think the missing is A comma D.
Oh, right. A comma D we have not considered. Thank you so much. Yeah, A comma D we should count. We left with this. Exactly. Thank you. So yeah, 13 should be there. So why I'm saying that, like why I was, so with A, B, C, D, you got anti-chains to be equal to 8, and with A, B, C, D, E, it's 13. Do you remember these numbers comes from something if you know? Okay, so basically if you try to do with A, B, C, sorry, if you try to calculate with the set A, with the set AB, with the set ABC, this should be 1, this should be 1, and this should be 2. No.
Fibonacci sequence.
Yeah, exactly. I'm trying to make it. So basically, this forms a Fibonacci sequence. So 1, 1, 2, 3, 5, 8, 13. So this is coming from here, and 13. So basically these anti-chains forms Fibonacci sequence. So you can try to verify if there is some pattern because of this is happening. You can try to prove that, but in general it forms a Fibonacci sequence. So you can always try to, so this you can see this is coming from so this is coming from induction. So basically this ABCD is a subset of ABCDE, and which has the same relation. So this is actually your subset of poset with the same relations. Okay, so you have this subset of that poset. So you can try to find a inductive formula, or prove by induction that this forms a Fibonacci sequence, because this just adds the previous one, like previous two. So just try to find if you can give a relation why this is a Fibonacci sequence. So yeah, the interesting fact is this forms a Fibonacci, the number of anti-chains forms a Fibonacci sequence. Okay, yeah. Okay. So let's move to the last question. Let n belongs to P, so you have given n belongs to P, and Dn is equal to m belongs to P, where m, so n belongs to P means this is the set 1, 2, 3, 4, the natural number set. Okay, positive integers. And Dn is what? Dn is all the elements m in P such that m divides n. So this is the divisibility set which we have seen in the second question, if I'm not incorrect. So yeah, so Dn is this. So for example, if you want to take let's say maybe 8, or maybe let's say 6, so it should be what? All the divisors. So 1, 2, 3 and 6 should be there. So this is divide sense, so you will take the same number also. So 6 you can take. So d6 is like this. Similarly, you can get anything, for any n you can write dn. So consider the poset dn. So this is the symbol for divisibility. Okay, it is not showing. 1 second. Oh, okay, sorry. Yeah. Okay. So what I was saying? So d6 is 1, 2, 3, 6, right? And this like vertical line shows that we are talking about the divisibility relation. So dn comma this divisibility sign partially ordered by divisibility. Consider d54. So we are talking about 54 here, d54. So firstly, can you tell me what is d54? Can you tell me the numbers? So all the numbers which divides 54. So you can always start with 1. Now, can you tell me quickly?
2, 3. And then 3, 6.
6, right? Oh, yeah. Yeah. 6, and then 9 should be there, right?
3, I don't.
Yeah, we can actually write it like this: 24 into 27 into 2, right? 3 into 3
18, and then other one is 18.
Yeah, 18. So you just take all the possibilities, 18, and then 27, and anything else, but directly just 54.
54, that's all.
That's all, right? Exactly. So number of divisors, you can actually, if you know the formula, is just 3 raised to power 3 into 2. So it should be, the number of divisors should be 3 plus 1, the power, so just write it in the prime power, and you can just actually calculate 1 plus 1. So you add 1 in both the numbers, like all the powers, and multiply. So you'll get 4 into 2, that should be 8. So if you have 8, 1, 2, 3, 4, 5, 6, then we are done. Yeah, you can always verify with this formula. Okay. So that is formula, that this formula is also very like obvious from the definition itself. So yeah, D54 is this. Now what has been asked, consider D54, find the maximum length of the chains exist in D54 divide by like this divisibility relation. So maximum length of the chains exist, so you need to search for the chains. So again, for the chains, what you can try to write divide, like you can try to form the Hesse diagram, because as I said, this is very like you can picturize easily in that case. Start with 1. Now what should I have? 2, 3. So I can actually take in the 2 parts, because next is 6, so it should come in the next step. So 6 is divisible by both, so this you have. And then 9, so 6 does not divide 9, so and 2 does not divide 9. And now you have 18 next, so 18, and even 18 and 27 can be in the same line, because 18 does not divide 27. So this you have as a relation, you have this, right? And next you have 54. Is that okay? So there is nothing in between for sure whenever there is a covering line. So is this Hesse diagram okay?
Okay, ma'am.
Okay, great. So you have this. Now you have been asked like maximum length of chain. Can you which chain you can consider? Like just check what all chains you can take, and you have to pick the maximal one. So can you tell me one chain? Maybe try to find the biggest one. So you are trying to find a subset of this Dn such that which forms a chain under the divisibility relation. So chain means everything should be related, like all the pairs should be comparable. So whenever you take two elements, there should be a relation between them. So when we say there should be a relation, so it's like a chain. Why we call it a chain? So for example, you have 1 is less than or equal to 2. So for example, you have taken 1 and 2. There should be a relation, right? Okay, I'll write it in the general sense why we call it a chain. So you have x and y. You are saying these are the elements of chain, so that means there is a relation. Without loss of generality, let's say x is less than or equal to y. Now you have next number z, so it should be related to x, it should be related to y, right? So you are saying there are 3 elements from the chain. Okay, so that means all elements should be related. So you have taken x and y, there is a relation, there should be a relation. So let's say x is less than or equal to y. Now you are talking about z. Now where z should fit? So you are saying x is less than or equal to y. Now it should be related to y. It could be like this, right? It could be like z is greater than or equal to y is greater than or equal to z. But in that case, there should be a relation between x and z also, because these are elements of a chain. So x and z should have a relation. But in that case, can you tell me what relation it should satisfy? You have x is less than or equal to y, and you have z is less than or equal to y. Can you tell which relation x and z should have in that scenario? So for example, if you take x is less than, so I'm just trying to say that there will be a chain of fixed direction, not like a zigzag one. Okay, so okay, I should frame my question like this. If x, y, z belongs to a chain, and x is less than or equal to y, and x is less than or equal to y, then, or maybe and y is greater than or equal to z, then we should get a contradiction. So what I'm saying, if you have x is less than or equal to y and y is greater than or equal to x, now for you know that x and z should be related, right? Now let x is greater than or equal to y. We will consider both the cases, right? Okay, let's take x is greater than or equal to z. With these two things, what will happen? X is less than or equal to y, and uh, yeah, I should take the other one. So you have x is greater than or equal to z, and what I'm doing.
X less than or equal to y.
Yeah. So maybe I'll write like this, because x is greater, z is greater than or z is less than or equal to x, and x is less than or equal to y from this relation. Then you should get z is less than or equal to y, which is a which is okay, right?
By antisymmetry, that will imply z equal to y.
Uh, by
Oh,
antisymmetry, no,
got y
it's
greater
okay,
than or
no?
equal to z. Okay, okay.
Yeah, I think it's okay. So this case is okay. Okay, I should not write contradiction. Let's see this one only. So you got, so let's check if can this possibility, like this is possible or not. X is, so this is first, this is second. Let's check about second. So you have x is less than or equal to z, and z is less than or equal to y. Then it should imply x is less than or equal to y. Oh, both are possible. Oh, right. Okay. Yeah, there is something. Okay. Oh, wait. Okay, my claim is I should write like this. So you have, if you have x is less than or equal to y, and there is some element z in C also, then either z should be like this, or you should have this. So basically all the elements should be in a chain. That is, like if you have, for example, x1, x2, x3, if you have some finite set, maybe let's say finite, this belongs to C, then either x1 is less than or equal to x2, either this should happen, or x1 is greater than or equal to x2. So if these are the elements of chain, then there should be a chain, that I want to say. So actually that can be proved for sure, because that's why the name comes from, so why we call it a chain. So what we have proved here, what I've taken, so if x is less than or equal to y, and y is greater than or equal to z, so there it should be here. Or maybe x is less than, oh right, all both the possibilities are possible basically. So I should take 4 elements to claim, to check it, because so basically if you have x is less than or equal to y, and y is bigger than z, so it could come in, wherever it might be. Like for example, it could be like this, or it could be like this. Both are the possibilities, right? both are both are forming a chain, right? So just try to prove. I'll explain next time rigorously. Like if there are elements in chain, then it should satisfy some fixed property. Like you can order it in a way, you will not get something like this, like zigzag thing. That I want to say. So just try to prove it, otherwise I'll explain next time, no doubt. So maybe exercise, or maybe I should write, you can number in a way. So this is not the way you can. Okay, so let's frame it in a better way. Then either xi1 less than or equal to xi2, xin, or xi1. So because it could be possible x3 is coming in the front, because we have not ordered the set earlier, so it's like this. where ij's belong to 1, 2, 3. Okay, and these are distinct. Like if you have ij, it's not equal to ik. Or maybe you can write like, yeah, we are just saying equal to also, so we can repeat it, but let's take it not equal thing. So just try to prove it. That is a general thing. Okay, let's come to our question. That was not related, but it's an interesting fact. So yeah, so that why I was saying that, because you just take a line. Now you just check a line, because there's a chain you want to check, you want to figure out. So you just take, for example, this chain you can take. You have this chain, or you can take this chain. Oh, is it messy? Yeah, I can change color. Maybe this. Oh, maybe dark. You can take either this. You just try to find a chain in this Hesse diagram. So here the biggest chain you can have 1, 2, 6, 18, 54, or you can take 1, 3, 9, 27, 54, or if I remove it, yeah. So or you can try, what you can try, you can go zigzagly like this. So you start with 1, so you go like 1, 3, and then you go 6, because there should be a relation. So you're just going up, and you can go like 18, or there is no relation other than 18 from 6, and then you can go like this. There could be one option, but if you are talking about the count, then you will only get 5 elements in the biggest one, 1, 3, 6, 18, 54. You can try 54, 27, 9, and you cannot go up, you cannot go to 18, because otherwise 27 and 18 will not be related. So you cannot go up, you have to check, like you are just going down and try all the relations. So you have 54, 27, 9, 7, sorry, 9, 3 and 1. That is one option. You have other option, 54, 18, 9, 3, 1 again, 54, 18, 6, 3, 1, or 54, 18, 6, 2, 1. These are four or five possibilities possible for the biggest one. Is that clear how we are doing that?
Yes, ma'am.
Yeah. So basically, if you prove this exercise, then you will be done. Just try to do it. It will be helpful. So that is the biggest one. So if you are asked, if the maximum length has been asked, then you can, so the answer should be just 5. So 54, 18, 6, 3, 1, whichever you choose among 4 we have. So we have the length should be 5. Okay, let's move to the next part. Can we write D54 isomorphic to some power set of a finite set? So let's see what has been asked. So question is asking, yeah, you have D54. Can you write it as an isomorphism to some power set of x, like 2 raised to power x? Can you write it like this, where x, so power set has the natural partial order relation, which is inclusion, right? That is the one we are talking about. X is a finite set, and it represents, or maybe denotes, the power set of x, and has the natural relation of inclusion. Okay, so this is the poset which has the natural relation of inclusion. So the question is asking, can you have such kind of an isomorphism with some power set? Okay, so here Hesse diagrams comes into a picture again. So basically, what should be true? So firstly, check whether a number of elements. So you know that in a power set, what happens in a power set? How many elements we should have in a power set? If you have, let's say, x is equal to cardinality of n, then number of elements in power set should be, sorry, this is other side. So number of elements in x is n, then how many number of like how many elements should be there in power set?
2 to the power n.
Exactly, very good. So first you check, do you have these many, like do you have a number of elements in D54 of some power of 2? Is it true always? This is not true always, because we never say phi n, so we are just counting the number of divisors. We never write phi n has to be a power of 2. You can check, for example, D18 maybe, like the number of elements should be, like you can write 18 to be something like 2 into 3 raised to power 2, so 1 plus 1, so power is 1 plus 1, and into 2 plus 1, so this is 2 into 3, so this is 6. It does not require to be a power of 6, so we fail there only. Like if you are asking, like if D18 is isomorphic to some power of 2x, you cannot write it because number of elements are not matching. You take any x, you will never get 2 raised to power, like you will never get D18 to be a power of 2. So number of elements are not matching, then we can directly say if that is that you can write or not. So for D18 it is not true. For D54, let's see how many elements we have. We had how many were there? 8, right? 8 is there, right? Exactly 8. 1 2 3 4 5 6 7 8. So you have 8. So yeah, you are, now you have to check because this is some power of 2. So there is a possibility, and there is one possibility you have to take x to be, the cardinality of x to be 3. So you are checking if D54. So the question is now to check whether D54 is isomorphic to 2 3, like sorry, not 2 3, to x, where or maybe I can write x to be just square bracket 3, where square bracket 3 represents 1 2 3. So you are asking just 3 elements. If you can show the isomorphism, then you are done. Now, so first property is checked because number of elements. So first property should be bijection. So you can always define a bijection, no doubt. Bijection between number of like finite elements. If you have like both sides, if you have same number of elements, then you can definitely define a bijection, right? Bijection can be done because number of elements are same. Now the second part comes. Second part says there should be, like whenever you have, if you define D54 to 2 3 some phi, then whenever x is less than or equal to phi in D54, phi of x should be less than or equal to phi of y in this power set. So it should happen for every x and y whenever this happens. So second property, this you need to check. Okay, so now Hesse diagram importance comes. So I'll just again snip. Okay, it won't. Okay, I can draw it again. So I'm constructing. So you have 54, 27, this was 18, you have 9, oh yeah, okay, 6, and you have 3, you have this relation 2, and you have 1. right? This was your Hesse diagram. Now let's construct for 1 2 3. So you have 1 2 3. So basically the partitions we are not part yeah okay. So you are talking about the subsets. So subsets you can have wait a second, what was the thing? Subset relation, yeah, 1 2 3 you can have, yeah, you can have 1 2 okay, 1 2 means this, you have 1 3, and you can have 2 3, right? Now you go down, you will get 1, sorry, yeah, what am I doing? So you have 1, basically you just write 1 2 3 here, and now just make relations. You have this 2 and 3, and here 5 comes. So this is your Hesse diagram for 1 2 3, like power set 1 2 3, power set for 1 2 3. So can you see these are not similar?
Yes, ma'am.
So here you can directly see and say that this is these are not going to be similar. So you can try to rigorously prove that, but basically what is happening with the biggest number, you should have 3 relations, but you are just getting 2, right? There are just 2 covers here, 18 and 27. Sorry, to cover 54 there are just 2 elements, 18 and 27, but here you are getting 3. Here itself it fails. So Hesse diagram is not same, like you cannot so basically number of relations should be, number of covers should be same. So here you have 1 2 3 4 5 6 7 8 9 10. Here you have 10. So 1 2 3 4 5 6 7 8 9 10, yeah. And here you are getting 1 2 3 4 5 6 7 8 9 10 11 12. You are getting 12 relations, right? If I've counted right, 3 1 2 yeah, there are 6 yeah, exactly 12. So there are number of covers are exactly 10 here, and here these are 12. So these are not going to be, any 5 you choose, you are not going to get what you need. So you can directly say from the Hesse diagram that these are not going to you cannot define isomorphism between these two sets. Yeah. Is there any question on this question?
No, ma'am.
Okay. So yeah, this was the last question for me. If you have any doubt, you can just tell me now.